So to understand these rigid body dynamics, we have to understand many concepts here one by one. So first we understood the translation of a particle, and then we proceeded to get the translation of the rigid body as a whole, because particle to body, right? And then we defined pure rotation, okay, and pure translation, combined motion, okay. Then the concepts of the axis of rotation, right, instantaneous axis of rotation and things like that, okay. Now we will have to learn some more concepts. One of them happens to be the angular momentum, very important. Angular momentum, we again start with angular momentum of a particle, angular momentum of a particle in a rigid body, and how it gets extended to the angular momentum of a rigid body. Angular momentum of a rigid body about the center of mass or the centroidal axis, and then angular momentum of the rigid body about any other axis, okay. And then we will subsequently develop the theory for torque. Again, torque on a particle, torque on a body, etc., etc., goes on like that. Okay, so these all have to get knit one by one. So I will go ahead with the angular momentum. Okay, friends. Hello. And angular momentum is not new to all of you, right? Angular momentum. I have already explained this sometime back, right? If you remember L, and before the physics teacher teaches you angular momentum, the chemistry teacher would have already used it, because the first chapter in chemistry will be Bohr radius. So there you would have written the angular momentum is integral multiple of the Planck's constant, isn't it? So you would have already done that, and so you would have come across that. Now the concept here is like this, See, we are going to now observe we start with the particle. We start with the particle. To begin with, you see, supposing I have a particle here of mass m having velocity v. Okay, just in this plane, and then you locate some point here. Okay, you say this is the reference point, and obviously you will. Okay, I don't have to write like this. So sorry. Okay, so you locate a point here. So this you coined as a reference point. This you coined as the reference point. Now the thing is, this particle, I will now reference the position of this particle by this position vector r. By this position vector r1. So with the reference point at O, I would like to now address this particle of mass m moving with velocity v, and together we can take it as mv bar, that is, let's say, the momentum of the particle. Okay, now what we do here is we define a concept called angular momentum here. We can define a concept called angular momentum. Why we define this concept called angular momentum is because this particle is, as you can see, is in motion. This particle is in motion. So this r bar vector that you see here will keep moving like this as it is tracing the particle. So you can see that. So, and one more thing what we do is we will now extend this line of action, and then we will also draw a perpendicular passing through this point. So you can see that this line, this dotted line, is passing through the line of action, and it is perpendicular to another line which is passing through O. Okay, and as you can see, this angle theta keeps on changing. Yes. Okay, so you can see that the momentum of this body. See, please appreciate and understand. The linear momentum, P is constant. It is not changing, right? Why it is not changing?
No external force.
No external force is acting. Excellent. And but you can see that but the linear, the body is in motion. So if you fix some reference point, its displacement is increasing. Similarly, if you see here, its angular position keeps on changing because theta keeps on changing.
Yes.
Theta keeps on changing. So therefore, the term angular momentum will come into picture, because now we will use this concept of that the as the body is traveling, we will measure the motion in terms of the angular measures, to start with, it appears, oh, what is this linear motion? Now you want to complicate it with theta. Well, I am sure you will not say so, because this theta will start playing an important role when we are really going to encounter bodies, when we have to consider them as rotating. We have to consider them as rotating. As you have seen that the concept of rotation is best understood when we draw a line on the rigid body, and if the straight line and with some reference line, if this straight line on the rigid body keeps on changing its angle, then we say the body is rotating. Okay, so that helps us to connect many things. Okay, so on and so forth. Okay, so that is the idea of developing this angular momentum, and the symbol used is L bar for this. P bar is used for linear momentum, angular momentum it is L bar, and as they say here, see now M V bar is equal to P bar. Already we are seeing many similarities between the angular variables and the linear variables. So here instead of P bar we have L bar, and we know instead of M here for angular motions, we will be using the moment of inertia. We are using moment of inertia.
Yes, sir.
Now you will see here, we can use the concept of moment of inertia here, and I will soon prove this has to be what? M. Okay, this will become what?
I omega bar.
I omega. Okay, you are right. I into omega bar. Okay.
Yes.
This will look like this. So on and so forth. Okay, we'll go into those details, right? Yes, because I have made all the printed things ready so that it can be easily comprehended. So better comprehension will be with these diagrams. Please follow the diagrams that I am showing here. Okay, so angular momentum of a particle. We begin with this. So you can see here there is a reference line O, and the particle in question is here at P, the position of the particle, and we designate this as R bar P with respect to O. So this is a good designation, that is R bar is always pointing towards P, right? And it is always referenced with respect to O. That means if the particle changes its position, R bar PO will also change, but the meaning will not change.
Yes, sir.
And you can see that the M V bar here is making an angle theta with the reference line, as you can see here. Okay, so this is another way to look at it. Anyways, okay, so to begin with, now M V P. So here velocity of the particle P with respect to O. Okay, that is also very clear, because to say what is the velocity of the particle with respect to O, that is also designated like this. So the component of the momentum along OP bar is M Vp over cos theta, and does not result in the rotation of O. Obviously, that is, if the particle is moving along this, then the angle theta. Okay, so if you take the component of this along this line, then as the particle is moving, the angular position of this with respect to this is not changing. So does not result in rotation about O. However, the component MPO sin theta, it is perpendicular to OP bar, result in rotation about O.
Yes.
I suppose you understood that. We'll split this into two components. That will result in the rotation. So mathematically, so we wanted to define this basically, we wanted to identify that, that with respect to the reference point, the particle is rotating. Okay, we wanted that thing to come, and it is fitting perfectly into the way we look at rotation. Okay, so so therefore, and the convenient way for this is that this observation this observation can be immediately put into the mathematical framework like this. So the angular momentum of P with respect to O is RPO bar, or the position vector cross m v p bar, or the linear velocity of this.
Yes, sir.
So because as you know, it is RP mv sin theta, okay, and mv sin theta is what we got it here. Okay, so other component simply vanishes. It has no role as far as the angular momentum is concerned. So the angular momentum of a particle, if this mv bar is moving along this line, then its angular momentum is what?
Only due to the perpendicular component.
It's no. If it is moving along this line, its angular momentum is 0.
Yes.
Because its angle is not changing.
Yes.
So its angular momentum is changing. That means you will only take the perpendicular component. Okay. So here we go. LPO bar is equal to RPO cross MV bar sin theta, where VPO is the tangential velocity with respect to. So we start using this concept of tangential velocity. See, these are all the way the concepts are getting knit, so that our understanding of the reality keeps growing in inches, but coming closer to the realities. Okay, so we start designating the perpendicular component as tangential velocity with respect to OP bar. Hence, hence VPO or sin theta. So, because we know that is this one. See, V is equal to omega r. In fact, it is V is equal to omega cross r bar. I hope all of us remember this.
Yes.
So now PPO sin theta will be equal to omega into r. Right? Hello.
Yes.
Yeah. So straight away we will get the omega term into our this one. So straight away we are able to write here LPO bar is equal to so and so into m omega into so. So we get here m r square cross omega. So LPO are equal to I naught into omega. That's how we arrive at it.
Yes.
Right? So now only thing is, you see, this is important for us. So when we are considering this angular momentum of the particle, then the inertial mass of this, that is, you see, m only stands for if you are only thinking about the translated motion. Okay, then rotational inertia is mr square. Hello.
Yes.
So therefore, you see, the concept of rotation will come into picture, and the concept of rotational inertia will come into picture, and the concept of rotation also comes into picture. So you see, it's all very nicely done, because you see, we have a mathematical framework for linear translation, okay, and we have for translation, and we have the model for the rotational motion, and both are similar in its expression, and that's how I used to say, yes, this is perfectly fitting. Okay, because developing the math models also, we should get a feel of the realities. Okay, I suppose we are all very happy that we got this diagram. So therefore, now these designations are important here, because why I'll tell you. See, when we defined the translation, and when we said the translation momentum and all, it was simply mv bar. We did not bother about with respect to what we are talking about it and all, but here it is extremely important, because if you, so this very clearly says, if you change the reference point, I repeat, if you change the reference point, then this quantity will also change. So L bar P with respect to O is equal to IO. IO stands for what? The moment of inertia about the point O, and
yes.
omega of the particle P with respect to O. So you can very well see,
Yes.
if we change O, then these quantities will also change.
Yes, sir.
Yes, sir. Yes.
So now this is where we have to start becoming more and more alert when we are dealing with the angular quantities. And another important thing is, you can see here when we wrote this equation, the direction of P bar and V bar were same. The direction of V bar and P bar were same. Okay, but here you notice that here omega bar, the direction of omega bar up, right? Hello.
Yes, sir.
And the direction of LPO bar will be same as the direction of the
Omega.
bar.
Yes.
Here also it is same, but only thing is omega bar, I suppose all of you know, it is up. That means if the omega is like this, it is anti-clockwise, then the omega bar will be perpendicular to that. I suppose you know this, and the same way this L bar also starts getting that's putting it up.
Yes, sir.
Yes, sir.
All right. So that is one way of looking at it. So I think it's clear from this diagram what we mean by the angular momentum of this particle with respect to O. So this line RPO, it follows the particle and its angle keeps on changing. That is another way of looking at it. And therefore, you will use the concept of angular momentum. Now the same thing, I am just putting it in the XY frame. I am putting this point O as the origin of the XY frame. And here I get one very good abstraction. What is that abstraction? This is V bar. So I extend this line and I extend this line, you get theta. And here I get this OQ. Okay? So, right? So now here you see what is the angular momentum of this? Angular momentum of this will be mv into OQ. See, if you extend V here, OQ will be perpendicular.
Yes, sir. Yes.
Okay, this is nothing but R sin theta. Right? This is also theta,
Yes, sir.
this is R. So this line OQ will be equal to R sin theta. Or in other words, if you extend the line of action of the momentum vector, okay, and then take a perpendicular from the point of observation or reference point, then this perpendicular distance is what matters.
Yes,
Yes,
sir.
sir.
Did you understand this?
Sir, I understood.
Yes, sir.
Okay, I think you will recollect something like this that I had already told you earlier. Okay? So let me just repeat that. Okay, so I have a line here. I have the origin here O. Okay, and I will also have a parallel line here. Okay, I will have a parallel line here, and there is a particle here whose momentum is P bar. Okay, so this is the point which is shining, and so this becomes R bar. This becomes R bar. Okay, and say this is theta. Okay, now this particle now keeps moving. This particle keeps moving up the line. It's a straight line. So at time t1 it is here, at time t2 the particle is here. But the momentum vector will be the same. So this line now becomes this. So initially it was theta1, now it is theta. Okay. So now do you say the angular momentum of this particle changed from here to here?
Yes, sir.
Yes, isn't it? Because theta has changed, it has changed.
Yes, sir.
Everybody agree?
No.
One person said no. Good.
No.
No, another person said no. Excellent.
No, sir. Yes, sir.
Yeah, another person now says yes.
Yes, sir. Yes, sir.
Because as I told you, this perpendicular distance will not change.
Yes,
This
sir.
perpendicular distance will not change. Okay? This perpendicular, so therefore the angular momentum of this particle with respect to this for this condition has not changed. For this condition has not changed. Got it? Why? Because you see, if you take this r, then this is theta, then this becomes r sin theta. So r sin theta is what? That is, I told you, you draw the line through the line of action of the velocity vector. Okay, and then you have this line drawn through it, and then what you have to do, you have to draw a line from this O to intersect this line of action such that it forms a perpendicular.
Yes.
Yes, sir.
And this one, what we designated as moment arm. Moment arm, we call it this one. So this moment arm is constant. Right? So it is mv bar into moment arm. Moment arm is not changing. Okay? See, r is increasing, theta is decreasing. Therefore, r sin theta product will remain constant. Okay? And therefore, the angular momentum is not changing.
Yes, sir.
Now, you see, this is also a bit of, a common sense, applying science. Momentum will change if you apply force. Right? Okay. Similarly, angular momentum will change if you apply something, some physical quantity. That is what we call it as torque.
Okay, yes, sir.
That is what we call it as torque. I'll introduce that to you. Anyway, you know that we have already used, but still, okay. And since no torque is acting on the body, okay, on this particle, so therefore the angular momentum also will not change. All right, friends. So these terms now, L suffix O and all, it's important for us, right?
Yes.
Now here is a wonderful diagram for all of you. You can now see that that an arbitrary body is chosen. Can you see here? An arbitrary body is chosen, and an arbitrary particle on the body is chosen. Can you see here? P is a particle on the body.
Yes, sir.
And you can see here that there is reference, and we have got x, y, z axis. Okay, and this particle P is referenced from a point here. From a point here. Now, what you have to understand is, this r bar, and you can see here dmv. What is this? dmv is what? dm is the incremental mass and v is the velocity. So dmv becomes what? The incremental momentum, linear momentum.
Yes.
Now these two vectors, which two vectors? dmv bar and r bar, they are in the same plane. Hello?
Yes, sir.
Yes.
Yes, sir.
And this plane is intercepting the a point. This plane is intercepting this axis.
Yes.
That is, what
Yes.
I'm trying to say is, see, this P bar and this, okay, this one. So I'm drawing a plane here, and then from the reference I'm drawing a line. So this plane that I'm choosing here is perpendicular to this line.
Yes, sir.
That's what you have to
Yes.
say. This is very important. This is perpendicular to this line here. Okay. So then you see, then this is from here it is r bar, and from this point it becomes what? rp bar.
Activity sector. Yes.
Or you can write it as rp with respect to O.
Yes, sir.
rp with respect to O, with respect to this point. Okay?
Yes, sir.
So therefore, the angular momentum of this particle P, which is a part of a rigid body. This particle P is part of a rigid body. See, the important thing is this rigid body is rotating about this point C. This rigid body is rotating about this point C. Got it?
Yes, sir.
Yes, yes.
Yes, sir.
And first we start with locating one of the particles of this rigid body, and we calculated its incremental angular momentum. You can see here dl bar. Can you see here?
Yes, sir.
DL bar. DL bar of this. That's what we said. Right. And then that is what you can see here on top. You can see here, my dear friends. DL bar is equal to R bar cross DM V bar. That is R square DM omega. Can you see this?
Yes.
Yes.
Okay. So what is this? This is the incremental angular momentum of the particle dm, whose angular speed is omega, and at a position r from this point on the axis of rotation. Okay. Now you see here, if you integrate all such dl bars, then you will get the L bar, and this axis I am designating it as Z axis. So L bar Z will be integration of dlz, that is equal to Iz omega.
Yes, sir.
Iz is what? Iz is what? The moment of inertia of this body about this axis. Hello?
Yes, 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 sir. Yes.
Into this entire body is rotating with omega bar. Got it? And you can see here that the LZ bar and omega bar are both coinciding.
Yes, sir.
Coinciding means along the same line.
Yes.
Okay? I hope you got it. All of you.
Yes, sir. Yes, sir.
Yes.
Right. While omega bar is a vector, Iz is not a vector, it is a scalar. Okay?
Yes, sir.
So we have now seen a particle in motion, its angular momentum over a point. Now we have considered a body, a particle in a body, and we first calculated dl bar of this particle, of a bigger body. And then we extended the knowledge of, or the mathematical framework of dl bar into L bar of Z. L bar suffix Z.
Yes.
Okay?
Yes.
So that is how the transition we have to follow. So from a particle to a body, and how the Iz, Lz, omega bar, how all of them get interconnected. Okay?
Yes.
So what you have to now appreciate and understand is this omega bar is same for every particle in the body.
Yes. Yes.
That is important. Okay. So we are considering the axis such that omega bar of each particle is same. Understood? So now please start involving yourself. See, we cannot take any arbitrary. See, I take a body, one particle is rotating like this, another particle is rotating like this. Then where is the axis of rotation of the body? Axis of rotation for this particle is this. Axis of rotation of this particle is this. Now you cannot have two axes for the same body. I mean, simultaneously you cannot have two axes. Okay, so that is something that you have to appreciate.
Then starting we studied that, sir, any line on the body other than rotation.
I expected somebody to have this confusion. You can have any number of axes, man, but simultaneously you cannot have any number of axes.
Okay, simultaneously.
Simultaneously, that's what I said. See, I take a body. I take a body and assume that one particle is rotating like this, another particle is rotating like this. Then where will you define the axis of rotation? Because the fundamental of axis of rotation is that all the particles are rotating, right? Means every particle is tracing a circular path, and the plane of each one is cutting the axis at right angles.
Yes, sir.
Okay, so that will not be satisfied if you take like this. That's what I said, and that's obvious that the moment of inertia axis, okay, will coincide with the direction of the omega bar of each particle.
Yes, sir.
Because that means now for every particle the axis of rotation is common, and for every particle omega is common. Okay?
Yes. Yes, sir.
Now, angular momentum of a rigid body about its center of mass. So here I have just chosen some arbitrary point here to define this concept. I did not say that that this here don't say C means it is the center of mass and all. I did not mean anything like that. It's just a under some arbitrary point to just give an understanding how the angular momentum of a body has to be considered. If we know the angular momentum of a particle, then from that how to go about doing this. That's it. Okay. Now